Okay. All right. Hey everyone. So today we're basically just going to spend time going over previous quizzes, homeworks, and exams. Um, Also, feel free to post questions in the chat log, um, the chat box, sorry. And also, if you have more detailed questions, feel free to come to my office hours tomorrow morning. I'll try and extend them for however long they're, maybe like 1 extra hour, if there are people who have lots of questions. But okay, so of course our focus for the day is the exam, and one other thing is that on Wednesday we won't have class, so you can spend more time preparing for the exam. All right, so before we start going over things like previous quizzes and exams, I wanted to give you a rougher idea of kind of a rough idea of what's going to be on the exam, since we've covered quite a few topics, maybe to help you focus your studying a little more. So the exam is maybe 75% done at the moment. Still have to write another problem, but now we roughly know what's going to be on the exam. So in particular, one thing that is definitely going to be on the exam is a kind of higher level question asking you, here's a new task. How do you go from getting the data for this task to training a model that can output predictions on this task? And it's a pretty general question that encompasses various different aspects of stuff that we've learned over the semester. So you're basically going to be asked to fully specify a model from the data pre-processing steps to the model building steps to what happens at training time and test time, etc. So there's really no like existing practice question on any of these exams that's like that. So I wanted to give you a heads up that you should expect something like that, and maybe it can help you focus your studying. Okay, so the other questions are all, I guess, a little more open-ended than the stuff that you have in the practice exams. There will not be questions like, well, let's see if I can find, wrong. Sorry, I opened up all these practice exams. Yeah, there won't be questions like this one. I know like most of the practice exams have this kind of question, but this is something that you could easily implement yourself on a Colab notebook to get the right answer. So it's not really something we can ask about. The questions will be more in line with a couple of the previous exam questions, so we'll go over that when we get to the exam part. Okay, so how much time will the exam reasonably take? Can it be done in a single sitting? Yeah, so it's going to be 5 problems, possibly 4, but likely 5 problems, each with multiple parts. It's going to look very similar to the practice exams in terms of length, and those were intended to be done in 1.5 hours, or 1 hour 15 minutes. I would say that you should be able to do it in a 2 hour sitting, and it certainly won't be taking 48 hours. So the 2-day period is just so you can pick what time you want to work on it, and be kind of flexible with your schedule. But yeah, it definitely is not going to take 2 whole days. What should we know about data pre-processing? I mean, we've talked about some methods of going from raw text to a format that you can put into your models, right? So there's the tokenization. There's maybe you want to I don't know, do some filtering on your vocabulary. There's also like how do you decide what examples in your training data are reasonable and what aren't. So there's lots of things that fall into the pre-processing category. It's basically anything that you might want to do to your data to make it cleaner and easier to model. I probably shouldn't say any more than that. It is, oftentimes specific to a particular problem or end task. Right, so there is also a coding question. I mean, it's not really a coding question. It is something that you could answer without any coding, but there will be a question with an associated Colab notebook, and it's there for you to, use it to do some analysis if that is useful for your answer. But it's not like you have to implement an entire model in a Colab notebook or anything like that. We'll basically give you a large amount of scaffolding code, and you might want to make some small tweaks here and there to analyze what's going on in that code. Yeah, this coding question is one of the things that we can actually feasibly give you in a remote exam that we couldn't in an in-person exam. So there's not really a practice problem for that as well, but I'll go over some of the similar ish and conceptually at least practice problems on the previous exams. How detailed if an answer is expected for designing model for the task? Yeah, so of course we don't want you to be writing like pages and pages of stuff, but basically every single important design decision that you're going to make in this process, from going from data to model output at test time, that's what you're going to need to describe. And for every single one of these decisions, you need to justify why you decided to go this route. So I don't know, maybe a couple paragraphs. It would be best to format your answer in a kind of list of, here are the things I did, and for each thing, why did I do this thing? So sorry, that's a kind of vague answer, but yeah, in general, most of these questions can be answered in no more than a couple of paragraphs, and many of them are just a few sentences each. Like you saw in the practice exams, I know my answers are usually very brief, but some of those complicated questions can be answered in like a single sentence. So yeah, don't write huge amounts of text. That's just going to make it painful for us to grade, and we'll be annoyed at those kinds of responses. Okay, so let me get into the review of previous questions, and let's go ahead and get started with some quizzes. So we had 5 quizzes so far this semester. We might have one more after the week after the exam, but yeah, all of the quiz questions are relevant to topics that may or may not be on the exam. So starting with quiz 1, and I think this is also a good review of the stuff we covered this semester. So quiz 1 is dealing with a couple of different things. It asks you to compare, oh sorry, this might be too small. It asks you to compare n-gram models to neural language models. And so this first question, you're given an unsmoothed 5-gram model. So remember, we talked briefly about smoothing, in particular add-1 smoothing, as a way of kind of getting some probability mass into unseen n-grams that are maybe occur at test time but don't occur in your training data set, and you don't want to give those test sentences 0 probability just because you didn't observe a certain n-gram at training time, right? So that was the intuition of smoothing. But here we have an unsmoothed n-gram model, which means that any n-grams that it didn't observe at training time is going to have 0 probability at test time, right? And so if you see the prefix we gave you here, rabbits flap their wings, this is kind of unlikely to be observed in a training data set, right? Rabbits don't have wings, obviously, so you would only write this maybe in some sort of creative storytelling type task. So you might expect your 5-gram model to have never seen this prefix before, in which case this probability will just be 0. And yeah, this is, of course, not going to be a reasonable estimate, because this is a grammatically valid sentence, and also it's certainly possible in some sort of fictional world. So the fixed window neural language model doesn't have these issues with unobserved prefixes, because each of these words is modeled by a dense real valued embedding, right? So rabbits is similar in the space kind of to birds, right, and to other animals. So your fixed window language model is going to be able to give you at least some sort of reasonable prediction given this prefix. So that was the general intuition here. The second question, why do we cache partial derivatives while doing backprop? If you don't understand this, you should rewatch the backprop lecture and go through those notes. But in general, if you're going from the topmost layer to the bottom, you're going to be computing, when you take the gradient of each parameter with respect to each parameter, you're going to be recomputing a lot of terms, especially at the bottom of the network. And so you don't want to be doing all those computations again and again at every layer, because they're shared across some of those computations. Those partial derivatives are used over and over and over again, so you want to cache them to avoid unnecessary computation. It's one of the fundamental properties of the backprop algorithm is this caching, right? So yeah, that was for this quiz question. Maybe at this point it would be good to look over just briefly some of these. Yeah, this question in particular. So this is from the 585 2018 exam, problem 3. And this question, actually, I should say, is probably not a very good exam question. I think only one person in the class got this right. So definitely not the difficulty that we were aiming for. But it does test a couple of different concepts that are related to n-gram language modeling. So here we have a trigram language model. We're using add alpha smoothing. So we talked about where alpha can be a different value, not just one. Because remember, if you do add one smoothing, you're stealing away a lot of probability mass from stuff that you've observed in your training data set. So here it says that you're training this language model on Wall Street Journal articles from 2003, and you're testing it on Wall Street Journal articles from 2004. So the first question says, plot the shape of the probability, note probability, not perplexity, of your training data set under the n-gram model as this alpha term increases from 0 to infinity. And so this is the standard plot that you would see when you're applying smoothing. Without any smoothing, you have maximized the likelihood of your training data set. You're going to be assigning a really high probability there. But as you add smoothing, as you make alpha larger, you're stealing away probability mass from the n-grams that you've observed in your training data set and putting them on unseen n-grams. Remember the 0 terms that were in the count matrix that we covered at the beginning of the semester. So we're gradually going to be decreasing the overall probability of our training data, because we're kind of taking away the mass and putting it on unobserved items. And you should also think about what happens if alpha goes to infinity, right? That means that all tokens will be equally likely, right? All n-grams will be equally likely, because that alpha term dominates the counts that we observed at training time. So this eventually converges to some low probability. So at test time, here, since this was a kind of tricky part, these articles are from 2004. The training data set was 2003, so you would expect new entities and n-grams and so on to show up in this this test data set, right? And so initially, with no smoothing, right, when alpha is 0, you're going to have a 0 probability of your test corpus just because of all these unobserved n-grams that you're going to see at test time. Now, the whole point of adding smoothing to your n-gram model is to increase the probability of held out data, right? And get around this problem of, well, there's unobserved n-grams, right? So if you add a little bit of smoothing to the unobserved n-grams, you can still take advantage of the training statistics that you got from your training data set. So that explains this bump. When you add a little bit of smoothing, you get an increase in your test probability from 0 to some non-zero probability. But then the same thing happens that happens at training time. After adding too much smoothing, you're gonna kind of even out the probabilities of all the n-grams, and that's just going to make this converge to some value. And finally, the third question was really easy here. It's asking you to plot the perplexity, and perplexity is just the inverse of the probability, right? So you just invert this curve to get the perplexity. And remember that perplexity is the lower it is, the better your language model. And I see there's a question about the perplexity. Like I said, it's essentially the inverse of the probability, so it's directly a function of the probability of whatever data you're evaluating over. But we talked about briefly perplexity as having these connections to information theory, specifically the branching factor of the model and the data that you're looking at. So there is an example, you can go back and look at it from the language model lecture, where we looked at this this simple task where you had a language model of digits and they kind of randomly occur, and your branching factor is like you have 10 different digits, they all occur with equal probability. So you get a perplexity of 10, which corresponds to the branching factor. But yeah, in general, it's the basic metric that you use to evaluate language models. Okay, so let me. Sorry, there's a bump because referring to this plot, because when you add a small value of alpha as smoothing, then you're not like stealing too much probability mass away from the statistics that you've got, the counts that you've got at from your training data set, right? So Wall Street Journal, right, in 2003 is going to be talking about a lot of the same things as 2004. Not only that, but your training statistics have encoded a ton of low-level, like, syntactic information, right? Like what is likely to follow a noun, or what is likely to follow a noun phrase, or this punctuation mark, or so on, right? So that's all important information encoded in your training data set, and you would expect it to carry over to your test data set as well, right? It's still written in English. So that's where the bump comes. You're going from 0 probability because of these unobserved n-grams to a pretty reasonable estimation of the probability of the test set with a low level of smoothing. But then the thing slowly, the probability slowly declines because as you add more and more smoothing, you're washing out those training counts that you estimated on your training data set. Why does the test set from 2004 start from 0? It's because we expect there to be n-grams in the 2004 data that are not seen at training time, right? So with no smoothing, if you observe an n-gram that isn't in your training set, you're just going to have a probability of 0 for the entire test set, which of course you don't want, right? So that is the entire issue with unsmooth language models, and that's why we are adding smoothing in the first place. So yeah, again, this question is it was not a very good exam question, so I don't want to spend too much time on it. But yes, just to answer the last question here, there are certainly n-grams in common to both the training and test data set, and that's why we expect to see this this bump, right? Because we expect the training statistics to be a pretty good model of the test set as well. It's just that the smoothing helps us out with the small, potentially small set of unobserved n-grams. Okay, so let us move on to quiz 2 now. Whoops, I did not mean to close that exam. Sorry, let me open it again. All right, so in quiz 2, we were talking about attention mechanisms. And so question 1 here is essentially just, did you watch the lecture or do any of the readings? But the bottleneck in the RNN, here specifically, we're talking about the RNN's hidden state is tasked with encoding information about the entire prefix that it's seen up till that point, right? So all of that information is getting stored in a single vector. And this can be pretty bad for a number of reasons, right? If you have a very long context, then you're asking a lot of this model to store all the important semantic and syntactic and discourse level information into a single low dimensional vector. The second thing is that we know these RNNs, just through the nature of their computation, have a recency bias, which means they have more information about tokens that occurred recently and less information about tokens that happened well in the past. So this is kind of related to the issue of forcing all of that information into just a single vector. Some of the tokens will be advantaged more than others. And so attention lets us get around this by essentially allowing us to access all of the hidden states in the past, not just the immediate last one. So you don't have to store all of the relevant information in just the last hidden state of the RNN. This question I think I answered on Piazza, but I will restate the answer here. Why are the query and key projections important in the transformer self-attention? It's because you want the you want to allow the attention to be somewhat flexible and not have the same score when a particular word is a query and another word is a key versus when the situation is flipped. So having these different projections allows you to have asymmetric attention based on whether a word is a query or a key. And in practice, you might observe that having the same projection, so just having the same embedding used as query and key, will put a higher weight on the word itself rather than other words in the sentence. You can think about this as if you normalize the dot product, right? If you take the dot product of a vector by itself and take like the cosine similarity with the normalization, it's going to have a similarity of 1, right? So this is kind of some intuition on why if you have just the same projection, you'll be putting perhaps more weight than you might want on the word itself, whereas in an attention mechanism, a flexible attention mechanism, you might want to allow it freedom to focus on any other word in the sentence and even ignore the current word. Note here that we didn't talk about the value vectors. The intuition behind the value vectors is kind of less clear. Sorry, I have a... Okay. My student and also TA Simong has done some analysis experiments removing the value vectors from transformers, and it doesn't really affect the performance on translation or language modeling. So yeah, practically speaking, the value projections probably just a way of adding more parameters to the model, but maybe not super important. All right, so let's move on to quiz 3 here. Okay, so again, question 1 here, pretty simple if you understand what a recurrent neural network is doing, but remember that the recurrent update equation has a dependency on the previous time step's hidden state, right? That's the part of the update equation, the h sub t minus 1. So just by definition, we cannot compute the hidden state at time step t without having already computed the hidden state at t minus 1. So this prevents us from parallelizing across like the entire sequence at training time. But the transformer, we can do this, right? Because there's no such dependency. This is each time step we're just attending over the stuff we've seen in the past. And so through the mask that we've seen now in a couple lectures, also in the coding lecture last week, that mask allows us to parallelize the self-attention computations at training time. And this is the main implementation advantage of the transformer, is that it's much faster to train than a recurrent model of similar depth, because you can do all these computations at parallel. And this is probably the major reason why people don't use recurrent neural networks as much in NLP anymore, because it's much easier to train these deep transformers. Okay, the second question here was kind of interesting. So this was testing your understanding of like model size, essentially, and the tunable parameters in a model. So here we had a sentiment data set that contained only 10 labeled examples. So this is an incredibly small training data set, right? Most of the data sets we've observed in this class, like Squad or NLI, they have on the order of 100,000 training examples. So here we have 10, which is basically nothing. So what else do we have? We have a pre-trained transformer language model. So possibly something like BERT or GPT or something like that. And this has been pre-trained on a ton of data. And so now we have two different scenarios. In the first scenario, we have a downstream model, which is a deep recurrent neural network, and it's randomly initialized. We're training it from scratch. But it takes as input these contextualized word embeddings that are derived from the pre-trained language model. However, all of the parameters of this recurrent neural network are trained from scratch using just the 10 labeled examples. In scenario B, we have very few parameters associated with our downstream model. First of all, the composition function here is just the average of the word representations you get out of the pre-trained transformer. And the only parameters that are learned on the downstream training data set of 10 labeled examples is the softmax matrix, which is going to be projecting the averaged embedding down to a two-dimensional vector for the binary sentiment prediction. So here, of course, you have far fewer parameters to train from scratch, just the weight matrix for the softmax. The language model parameters are not fine-tuned. Note that in scenario A, we're also fine-tuning the language model parameters. So in general, scenario A is going to have orders of magnitude more parameters than scenario B. And when you have a very small training data set, you want to limit to as much as you can how many parameters you're training from scratch and how many parameters you're actually updating using this small data set. So scenario B is definitely to be preferred here. Because, and that's not to say that scenario B will work. Scenario B probably won't work, but it has a better chance of working than scenario A, in which you're very quickly going to overfit the 10 labeled examples, and there's no way this model is going to be able to generalize to any held out data set. There's just far too many parameters for that generalization to happen. You're going to overfit very quickly, and your function that you learned is not going to be useful. That's probably going to happen in scenario B as well, but the chances are definitely higher that there will be some generalization. Okay, so that was quiz 3. Again, if you have any questions, feel free to ask in the chat. Let's move on to quiz 4. So in quiz 4, the first question here is talking about the Electra model. So remember, this is one of the advances over BERT that we talked about. The other models that we talked about here were Roberta and Albert, and also the Transformer XL or XLNet. And each one of those had a couple of differences from the normal BERT model, improving on certain dimensions, like whether it be able to adapt to longer contexts, or able to be trained faster, or some small tweaks like Roberta that when combined together result in pretty significant improvements. So you should know all of those models and generally what their main contributions were. But this question in particular is focused on Electra, which used the objective of sampling. Instead of masked language modeling, we're going to replace some words in an input with other words, fake words, and then ask the model to do this binary classification task of, given each word in the sentence, was it part of the original sequence or was it a fake word that was added in? So in this question, we are asking about a different strategy of getting the fake words, right? In the normal Electra model, we have a generator model that looks like BERT, basically, that gives us fake candidate words that are kind of similar to the word that we're replacing, maybe similar in semantically or also in syntactically. And the question asks us, if we just randomly sample fake words from the vocabulary instead of using this generator model, what is going to happen? And so here the answer is just that if you randomly sample words, fake words, your task is going to be incredibly simple most of the time, right? So if you take this sentence, imagine if the fake words did not come from a generator model, and let's say I decided to replace the word come with cat, right? Just some random word. Now I have the sentence, imagine if the fake words did not cat from the generator model. If I have a discriminator that's trying to predict if a word is fake or real, this word is clearly out of place here, right? It's syntactically out of place, right? It's not a verb. Semantically, it doesn't really make sense with the context here. And so the model doesn't actually have to learn all that much about the sentence and the meaning of it in order to decide that cat doesn't belong here. If I actually used a discriminator, a generator model, then maybe this word would be something like, I don't know, follow, which still seems a little strange, but is much closer to the original meaning, right? So the model actually has to, better model what is going on linguistically in the input to predict that follow was a fake word here. So we would expect downstream performance, of course, to tank, to decrease if we randomly sampled words, because our model isn't going to be learning as much about language. All right, so for question 2, here we had a downstream sentiment task. We had access to a BERT model, and this question was about the intermediate fine-tuning process that we talked about in one of the lectures. So remember, in intermediate fine-tuning, we start with our pre-trained self-supervised task like BERT masked language modeling. And then we fine-tuned this model on intermediate tasks using labeled data sets like NLI or Squad or other data sets that we've talked about in this class. And then eventually we fine-tune it on our downstream data set. And so depending on a bunch of factors, like how related are these intermediate tasks to the downstream task, how complex are they, how large are they, if you choose the correct intermediate task, you can further increase your performance on the downstream task. So here we had a sentiment task, and we decided to fine-tune this model sequentially on Squad, then on Hotpot QA, and then on MNLI. And then eventually, after all of that, we fine-tuned it on our sentiment data set. And we found that this model is far worse than just a baseline where we fine-tuned BERT on our sentiment task. So there's a couple of things going on here. One is that none of these tasks are explicitly focused on sentiment, so they might not be very related to the downstream task. But the more important thing is that here we're sequentially fine-tuning on 3 different intermediate tasks. So each time you do this intermediate fine-tuning, you're going to be forgetting some information from your pre-training task, right? And we know that the pre-training in BERT is the largest contributor to our increases in downstream performance. It's the thing that allows us to encode the most linguistic, like generalizable linguistic knowledge, right? And so if we specialize our model to QA tasks and then also specialize the resulting model to entailment, we're going to have forgotten a lot of important information from our pre-training, which might have been useful for sentiment. And so this is why you don't want to kind of chain these intermediate tasks together like this. Every time you do fine-tuning, you lose information from the pre-trained task. And if you do it too much, you're going to lose a lot of information and thus decrease your downstream performance. Any intuition for why intermediate fine-tuning might lead to better performance on small data sets? So it really depends on the relationship between the intermediate task and your tiny downstream data set. But yeah, I mean, in general, yeah, I mean, I don't think I have a good answer, like general answer to this question. It really does depend on the relationship between the intermediate task and the downstream task, because you see huge variance at small downstream data sets, right? Some tasks really tank the performance, other tasks increase it a lot. So I don't know if there's any general finding here. It's just that on small data sets, your variance is going to be much higher. And so if you can get a good intermediate task that is kind of related in the types of reasoning that's required for the downstream task, or is related in the domain of the data or something like that, that can help offset some of the issues associated with the smaller data set. But yeah, it doesn't always help. So sorry if that was an unsatisfying result, but it's just not known, I guess, at the moment. All right, moving along here, final quiz. This was on text generation. The first question here was more of a kind of open-ended opinion, maybe, rather than a real problem, but it was talking about GPT-3's few-shot learning performance, specifically on these arithmetic problems. So they showed that GPT-3 can learn addition to some degree, especially with smaller numbers. Then they did this experiment to search for whether they had observed a lot of these examples in their training, their massive pre-training data set. They found that 17 out of the 2,000 addition problems occurred in this format in their data. Personally, I think that there are likely many other formats in which addition could be described in the training data set. There could be many paraphrases of these kinds of templates, and I think there's likely far greater or far more examples of addition problems in their data set than what they could find with these simple regular expressions. So I'm not personally convinced, but you could disagree. Yeah, this problem is not like anything you're going to see on the exam. It was more of an opinion. The second question, though, is more relevant. So here we had a new task of paraphrase generation. A model received a single sentence as input and is asked to generate a paraphrase. Right. So again, a paraphrase is a sentence that has that kind of maintains the semantics of the original sentence, the meaning of that sentence, but it's the surface form, like the words and structure, could be different. So the question asks, why might you want to use a sampling-based decoding algorithm instead of beam search here? And in this case, if you want to generate a paraphrase, you likely want some modification of the words or the structure, right? Otherwise, you're going to just decode the same sentence. So if you use beam search, you're very likely to copy significant portions of the input sentence in this task. And you're not likely to get much diversity when you decode using beam search, right? What is like the highest probable paraphrase of a sentence? Well, it's going to be usually something that's very, very close to the original sentence, if not identical. Maybe you just flip a word here and there. But if you use sampling, because of the randomness that's in this sampling strategy, you're going to have a much higher chance of getting different words from the input, much more diverse paraphrases. And this could be very useful for many downstream downstream tasks. Like if you're using paraphrase for data augmentation, as you did in your homework, here you might want diversity rather than copying your input. So that's a concrete case of where diversity is important in this paraphrase setup. Okay, so I see a question. In the homework, my model worked better when fine-tuned on MNLI than when fine-tuned on Yelp, but I expected Yelp to be more relevant as it was a sentiment data set. Was this expected? Yeah, that's interesting. So I think, first of all, there shouldn't really be expectations with these kinds of methods. They're very new and unexplored, and it's very possible that if you fine-tune on Yelp, you're not adding much more information to your downstream tiny SST data set, right? You're capturing a bunch of sentiment-related words and terms and keywords in the Yelp data set, but maybe you were already doing a good job of that with your pre-training, right? MNLI, on the other hand, if you fine-tune on that, you might have a better model of the semantics of the sentence in general, right? MNLI is testing essentially semantic understanding. So that could be much more helpful for in terms of what you're missing from both pre-training and from the tiny SST downstream task than just the Yelp data set, where the model might be focusing on sentiment related keywords and their associations to particular labels. But yeah, I mean, again, this was a very open-ended question. Depending on how you set this up and your random seed and so on, you might have observed different results. And you can come up with a reasonable explanation both ways. But it was just trying to get you to think critically about your results. All right, so wow, 45 minutes gone by. Let me move on to the practice exams and just go over some of the problems here. So starting with the 585 midterm. So we did not cover word devec or static word embeddings in this class. So there won't be any questions like this that ask you to compare different word embeddings together. like Elmo versus Word2Vec. So we didn't cover HMMs, we didn't cover the Viterbi algorithm. This is a nice problem about perplexity in n-gram models. Yeah, so I see there's a bunch of variants in results on this homework problem in the chat box. And the final message here, tiny SST is tiny, so maybe by luck as well, is a huge factor here. It's such a small data set that literally any outcome is within the range of possibility. And it's why, like, if you can do just one thing in a downstream task to improve your performance, the best thing you can do is just collect more training data. That's always going to be most helpful if it's possible. And all of these other things, like data augmentation, intermediate fine-tuning, those are only techniques that you should resort to if it's really hard or expensive to get any more labeled training data for your downstream task. All right, so this question is just asking what is a true statement about perplexity in n-gram language models. And so if you look at choice A, given a large enough training data set, perplexity increases as the prefix size, the order of the n-gram model, the n increases. This is false, of course. Your perplexity you would expect to decrease as you add more and more information to the context. Of course, at some point, without proper smoothing, you might expect the perplexity to start increasing again, but from going from like a bigram to a trigram to a 4-gram, 5-gram model, given enough data, you should expect to see perplexity decreasing. So this is false. Statement B is also false. You can only use perplexity to compare models of the same order. This is not true, right? All of these models are giving you a probability of your of whatever data set that you're applying it to, and those are comparable. Statement C, applying add-1 smoothing to an n-gram model results in increased held-out perplexity complied. So we didn't talk about absolute discounting, so we can ignore this statement. If your held-out data contains n-grams that are unseen at training time, your perplexity will be undefined unless you apply some form of smoothing. This is true. Smoothing is what helps you get around the zero probability, and remember, perplexity is the inverse of the probability. All right, we did not cover logistic regression or naive Bayes. I think for this exam, it is important to understand at least how we solved these problems. You should be able to come up with these answers, even though I'm telling you that you're not going to see a problem like this exact, like here's a network, compute these partial derivatives. The problem that you will see on the exam requires basically the same level of understanding. So you should be able to solve this kind of problem. Okay, so this problem, wait, was this the right? Sorry, this is a 2019 one. I'll come back to the 2018 one in a bit. This problem is maybe more indicative of the type of problems that you'll see on the exam. So here we're giving you a new task. Text infilling was not a task that I covered during the semester of this this class. Sorry, the 585 class that this exam is from. I also didn't cover this in this semester either. So this is an example of a new task that requires you to generalize some of the knowledge that we've discussed so far to something that you haven't seen before. So in this task, you're basically given a sentence and some number of blank words in the middle of the sentence, and you're asked to fill in the blank. So in the first part of this question, we're given a pre-trained left to right recurrent language model. So we're not given something like BERT where we can, mask out these tokens and predict them. Here we're given a left to right language model. So if we're given a left to right language model, how am I going to use it to solve this problem? And the key point here is that computational efficiency is not a concern. So we can use any algorithm regardless of how expensive it is. And the problem asks us specifically to produce the missing token sequence with the highest probability. So this is saying that we can't use an algorithm like greedy search or beam search, right? Because those are just approximations, right? They don't give you the exact argmax solution of the, like what is the highest probability continuation. Here we're specifically asked to get the highest probability continuation. So the only way to do this with our language model is to try every single combination of words in the blanks. We don't even know the size of the blank, so we have to try all combinations of 1 word, 2 words, 3 words, 4 words, so on, up to whatever k is. And for each completion, we have to measure the probability that is given to that completion by our left to right language model. So we know how we can use the language models to measure the joint probability of a sentence, right? We just multiply the conditional probabilities together as per the chain rule. And then once we've exhaustively enumerated all of the possible completions here, we're going to pick the one with the highest probability. So essentially here, this was a kind of combination of the decoding algorithm has to produce the highest probability completion, so you have to enumerate everything because all the decoding algorithms we've seen in the class are just approximating that argmax. Now, the second question kind of follows from the answer of the first question. Obviously, enumerating all possible completions is going to be way slower than greedy decoding, right? The advantage of greedy decoding is it's fast. I'm going to be predicting, just taking the argmax at every time step and using that as the model's prediction. I'm not actually going back and trying to revisit previous token predictions. And I'm not considering the entire space of possible completions or outputs. This problem, question 3.3, is also related to the question on the homework one, where we had you actually basically try this out with BERT model. So here, we were trying to use BERT for this infilling problem. So to do this, you would replace the blank with mask tokens, right? So Sarah went mask, 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 and put on her safety goggles. This problem is actually asking you to do the same thing that you did in homework one, where you take the argmax prediction at each of these mask tokens and use them to get your completion. So and now that I'm thinking about this, if you had read this practice problem in solution, you could have just copied it for homework one. So anyway, hopefully you guys actually understand why this is the answer. Each of these predictions is happening independently of the others, right? So I don't know if I predict 2 here in this mask token, and I'm trying to predict what's happening here. I am not conditioning this mask prediction on the fact that I predicted 2 for this mask token. So I don't have any internal coherence between any of the mask tokens in this approach. And so if I wanted to fix this, I would do one prediction at a time, right? So maybe I give this input and I just predict the word at the first mask token. So maybe I predict 2. So then once I have my new sequence, Sarah went to mask, 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 and put on her safety goggles. I would feed this into BERT again and predict what happens at the mask token for this mask. So maybe I get the. So then I feed in Sarah went to the mask, mask, and get the prediction for the third mask token, and so on. And in this way, I allow the model to condition on its previous predictions. So I would expect to have some internal coherence between the masked sequence. So that was the answer to this question. And moving on to question 4 here. This was also, I think, a relevant question. Here we're focusing on attention mechanisms applied to recurrent neural networks. And specifically, we're focusing here on target side attention. So we discussed the target side attention mechanism for recurrent neural networks. Essentially, it's the same mechanism that you use, attention mechanism that you use for recurrent neural language models. This was just laying out the equations of standard encoder decoder model. You have your encoder RNN, your decoder RNN, your softmax layer. Here, our softmax layer is going to be taking in as input the current decoder state at whatever time step we're at, the representation from source attention, which we've already defined in this this problem statement. The model has source attention, which means the decoder is able to look at all of the tokens in the all of the hidden states of the encoder. But now we have this target side attention representation, which means we're going to have basically allow the decoder to focus on previous words in the target sequence. So why would you want to do this? And we know, since this problem is focusing on RNNs, that the RNN language models have this recency bias. So adding this target side attention could help on longer sentences where we don't want the decoder to forget about things that it's decoded at the very beginning of the sequence. It could also allow us to focus more on like names. We talked briefly about the copy mechanism as a way of kind of copying rare words that we've seen before, because we're maybe more likely to produce them again. And the second question is very straightforward. It asks you, if you're going to implement target side attention, what should be the keys? Because we know in source attention, the keys are all of the hidden states of the encoder. But in target side attention, the keys are going to be all of the hidden states of the decoder up to and including the time step that we're currently at. So that's the D variable here is referring to the decoder's hidden states. And so the probably trickiest question here was question 4.3. Not a lot of people got this one correct, but it was asking if you can parallelize the target side attention computation. And if you look at this equation, this is stating that the target side attention is computed and only affects the prediction in the softmax layer, right? It's concatenated to the decoder time step and the source attention, but it does not influence the decoder's computation, right? There's no usage of the target side attention term in the decoder update equation. So that means that I can compute all of the hidden states of the decoder using my decoder update equation as I would normally. And then I can compute all of the target side attention representations at one shot using the lower triangular mask like we've seen in the transformer. So in the exact same way, I can compute these attention representations in parallel. Because I've already computed all of the decoder hidden states. And so I have all of those, so all I have to do is apply this mask to make sure that I'm not cheating and looking at things that come in the future. So this is a pretty tricky question, but yeah, it's basically, the answer is the way it is because the target side attention representation is not included in the computation of the decoder's time step. Okay, and finally in question 4.4, we were looking at you build the above model and deploy it, and your boss tells you that it's too slow, so your boss asks you to remove the encoder RNN completely. If you do this, then you're left with just the word embeddings of the source words on your encoder side. So the question asks why this model is not producing good translations. And it additionally asks you to give one solution to improve it without adding any learned parameters. So here, if you remove the RNN encoder, there's no longer any positional information among the source words, right? You just have a sequence of embeddings, but when you do source attention, there's no way for the model to tell that this is the first word, this is the second word, and so on. So remember, in machine translation, it's oftentimes, if you're producing the first word in the target sentence, you're likely to be focusing your attention on the first word of the source sentence, right? Because there's these common word alignments between languages. And so you lose all of that ability if you get rid of the encoder RNN. There's no positional information among these embeddings. And so one solution without adding any learned parameters is to just add these kinds of parameter-free position embeddings like the sinusoidal function of the transformer, right? There are no learned parameters associated with that. It's just a fixed function. And that could help you get some positional information on these word embeddings. Okay, so just moving along, because this is already 1 hour. We didn't talk about hidden Markov models or log linear language models. So that does it for this practice exam. Moving on to the 690D practice exam. Here, some of the multiple choice questions are relevant. We didn't talk about the importance of the scale dot product too much in this class, but essentially, I think there was probably one slide on this, that as you get higher dimensional vectors, the average magnitude of your dot product is going to be higher and higher, which can make the extremely large values dominate even after the softmax. And so adding the scale helps prevent this problem. So we're not going to be asking you, there are no multiple choice questions on this exam, and we're not going to be asking you questions that you can easily look up like this. Okay, so here there's a question about models that are sensitive to word order. Of course, the fixed window language model is sensitive to word order, right? This is the one where you concatenate the word embeddings of the past n words together and then put them into a feed-forward layer and then a softmax to predict the next word. But here, like you have a separate set of parameters for each position, essentially. So you do model word order. Wow, a new subscriber. How nice. Okay, so obviously n-gram language models also model word order, right? If you think about a trigram model, I'm modeling all combinations of bigrams as a prefix, so all 2-word prefixes. And so I'm taking into account the order of those words in the prefix. And when I do something like an element-wise average, I'm throwing away the word order, right? That's one of the downsides of doing these element-wise computations. Okay, so here's a question about beam search. We did talk about beam search. Basically, when we're doing text generation, beam search is oftentimes a better solution than greedy search. And so here it asks, like which are true and which are false. Beam search results in slower training time than greedy search is obviously false. We don't use either of these decoding algorithms in training time, so there's no impact. Beam search usually leads to higher BLEU scores in machine translation than in greedy search. This is true. Greedy search has a number of weaknesses. You're not modeling the probability of multiple paths. You're just, if you make a wrong decision early on, you're going to be, you're going to have a bad translation. There's no way to recover from that. So this is true. Beam search terminates after a fixed number of time steps, or if all paths end with an end of sequence token. That is true. Those are the termination conditions of beam search. Beam search is guaranteed to find the highest probability target sequence. We know that this is false. Beam search is a search algorithm. It's going to find you an approximation to the highest probability sequence, but it does not enumerate all possible outputs, so it does not give you it's not guaranteed to find the highest probability sequence. All right, moving on here. This was basically asking you to, like, what is the difference between a model that does not handle word order in the input versus models that do? So an LSTM is an instance of a recurrent model that is able to obviously handle the order of the words in a sentence. So here there were sentences with negations. So here we see, like, here was the first part of the sentence was negative, of course. It was predictable and poorly put together, but the overall sentiment of the sentence is positive, right? The film, nonetheless, despite all of these flaws, made me feel happy. So here, if you just averaged all of these words, you have negative words like predictable, poorly, and maybe one word, happy. You might not expect a bag of words model to get this right, but an LSTM could learn that this is kind of negated by the second part of this sentence. And the same kind of thing happens here. Here you have a but, a contrastive conjunction, which is kind of also negating what happens afterwards, where you have all this negative stuff, right? Clunky dialogue, lapses in logic, but it moves fast enough to overcome all of that. So this is a complicated sentence that a bag of words model would struggle with. All right, this question is talking about recurrent neural language models. Here and this is, again, one of the things that you might expect to see on your exam, where you have this hypothetical situation of you're training your model and you notice something weird about it and you're trying to explain it. So here you observe that the training perplexity of your LSTM language model is increasing after every training epoch. Why is this happening? And the reason is because the learning rate is too high. Out of all of these reasons, this is the only one that makes sense. And we talked about what happens if your learning rate is too high, right? If you remember that simple gradient descent visualization, if your learning rate is too high, you might overshoot the minimum of the function and go to somewhere else in the loss surface where you might actually have a higher loss. So tuning your learning rate is important to avoid these kinds of phenomena. All right, another backprop question we'll skip over. You should know how to do this. This question was very tricky. This is, again, an instance of a question that you might expect to see on your exam. Here, you're given basically an averaging embedding model for sentiment classification. You have this composition function which averages all the word embeddings of the input, then applies the ReLU function, which, remember, makes everything that's negative 0, and then is the identity function for all positive values. And you feed the resulting vector A to a softmax layer to predict the sentiment. So this is a very, very synthetic task, obviously. There's only one training example. The movie was awful, which is paired with negative sentiment. So you would never want to do this in practice, but it's a good exam problem. So you're training your model on just this single training example. The movie was awful, negative. And you're training it from scratch using random initialization of your embeddings and your weight matrix. And so here we give you the random initialization, and unfortunately the model never converges and is never able to overfit the example. And the reason here is because, I mean, it's testing your understanding of these activation functions. If you average all of these vectors associated with the words in the sentence, the resulting value for every dimension of the average vector is going to be negative, which means that this A vector is just going to be a bunch of zeros. And that means that no gradient is going to be flowing through the A vector to your W matrix. So nothing, to your word embeddings are never going to be updated because there's no gradient flowing through them. And so this means that these are never going to change, which means your average will always be negative, which means A will always be zeros, which explains why you're never able to overfit the single training example. So this question tested both your understanding of activation functions as well as gradient descent and backprop. And yeah, very, I guess a small percentage of the class got this right. Okay, and the second part of this was just how can you ensure that this doesn't occur without changing any aspect of the model itself? And the way you would do this, one way at least, was to just change the initialization. So you randomly initialize your model and then just add the minimum value in the embedding matrix to every element, which ensures that all of the embeddings are positive. Which means that this issue won't happen, at least for a while during training, although it certainly could happen at some point in the future, but at least you would be able to get some updates to your parameters in. Okay, and now this question, this one you should definitely understand. I guess I can say now there will be some question related to masking and the decoder of a transformer, right? This is very important to understanding why the transformer is so popular today. This problem again was very difficult for the class, but here you're doing machine translation, and this question is essentially asking you what happens if you use a modified decoder mask. So here, all of this modification is happening at the decoder. We're going to add an extra beginning of sentence token in the input to the decoder to ensure that the output and input are the same size. And now the decoder mask is modified from the standard lower triangular mask that we've seen in the transformer to this mask, which you can see the rows here, every other row is different, but adjacent rows are the same. So here, here the first two time steps are masking out the exact same tokens in the decoder. The third and fourth time steps are also masking out the same words. And the fourth and fifth time steps are also masking out the same words. So let's take a look at what is actually happening here. Since we've added this extra beginning of sequence token, if you look at the first and second time steps here, I'm predicting the word sum and the word cats. And I'm doing this with, if you look at the mask, the only tokens that are unmasked are the two beginning of sequence tokens. So based on that, I'm predicting sum, and then based on same unmasked input, I'm predicting cats. So if you think about this, compared to my normal decoder mask, when I predict cats, I no longer have access to the word sum, right? And that's the key difference between these two masks. For the second prediction here, where I'm duplicating the same mask sequence as the previous row, I'm missing a word that I in the standard case would have access to. So let's take a look at what happens when I'm predicting R and Fluffy. So here I have access to the first four tokens, beginning of sequence, sum, and cat. And that's fine when I'm predicting R, right? But what happens when I still have access to the exact same sequence of unmasked tokens? Did it reconnect? Okay, I think it's working again. Sorry about that. Please let me know if it's buffering or something. I don't know why the connection just died. Okay, so the solution here is just stating what I said before. Decoding is now proceeding in these 2-word groups, where each word is depending on all of the previous groups, but there are no in-group dependencies. So it's kind of similar to the issue that we discussed with the infilling problem, which I guess was not on this exam, where there's no coherence between token predictions in the same group because I don't have access when I'm predicting fluffy to the immediate preceding word. And now there were a bunch of questions about the effects of doing this. As an aside, this kind of decoding is called semi-auto-regressive decoding, in case you want to read about it. It is actually something that is done if you want to speed up your decoding. Is the mask also applied during cross-attention? No, this is only applied to the decoder side self-attention. We don't apply masks during cross-attention, right? Because we have access to the entire source sentence. It's not cheating to look at the whole source sentence. It's only cheating to look at words that we're going to predict in the future, of course. And that only happens in the target language. Okay, so let's look at these questions. Do you think Alice's model will improve translation quality? We already discussed that it will actually decrease translation quality because we're breaking some of the dependencies between words. And we're losing the coherence between words that are in the same group. Can this new factorization be used to speed up training time? The answer to this is no. If you look at it, we're actually probably increasing the training time because of the added tokens here. We've added a beginning of sequence token and a padding token. So we're still doing the exact same computations. We've only changed the mask. That doesn't affect our training time at all. The key question here is, can this be used to speed up test time decoding? And this was the trickiest part of this problem. This factorization does actually allow you to speed up test time decoding. And why is that? That's because if you notice, you can actually decode 2 words using the exact same input here. So you no longer have to wait before. Let's say I'm predicting fluffy. Normally, I would have to predict some cats are before I could predict fluffy, right? But due to this new masking strategy, I'm predicting fluffy conditioned only on beginning of sequence, some cats, right? I no longer depend on the word R to predict fluffy. So that means I can predict both R and fluffy in parallel because they depend on the same tokens, which means that I'm actually predicting 2 tokens at one time step, which dramatically, it speeds up my test time decoding, right? Because now I can predict 2 tokens using the same mask. And so I'm going to have fewer decoding time steps as a result, right? I'm going to have half the number of decoding time steps in this example. So that was a tricky problem, required a pretty solid level of understanding with what was going on here. Okay, and we'll skip this one since it's all about comparisons to WordDevec. And finally, I just wanted to look at the last exam. I don't think there's too much that was relevant here. A lot of this was about stuff that we didn't cover in the class. There's one question about the bottleneck problem in sequence to sequence. There's a bunch of false statements here, right? The vocabulary size of the decoder is obviously not increased if you add an attention mechanism. They don't allow you to interpret things by, so you are able to look at the attention weights, but that doesn't help you solve the bottleneck problem, right? These 2 things are orthogonal to each other. They don't increase the size of hidden layers as well. So the correct answer is that all of the encoder hidden states are incorporated into the decoders at every time step. All right, so we'll skip. This one is irrelevant. here's one that is relevant to our course materials. So Jill trains a deep averaging network that's just element-wise average followed by some feed-forward layers for sentiment. And her network has 4 layers, each of which has 256 hidden units, but she only has 500 training sentences. This problem was another example of overfitting, as we've seen in some previous questions. She had a very large network and a very small number of training examples. So she could make her network smaller to avoid overfitting. She could initialize her network or use things like BERT to get rid of the number of parameters she's training from scratch. She could get more training data. She could regularize her network. These are all valid solutions for Jill. Fairly straightforward problem as long as you're able to recognize that her network is overfitting, which is the cause of the problem. Okay, this is the problem that we went over from before. Yeah, and none of these other problems are relevant. All right, so regarding the homework 1, I guess I can open that up, but I think I only went already went over the most relevant problem here. Definitely do not want to click this. All right, so let's go to the homework solutions. I mean, most of this homework was implementation, so of course it's not going to be useful for the exam, but this question in particular with the multiple mask tokens in a row was something we already saw in the text infilling question. So this one was definitely relevant. And I think all of the other questions were more empirical, so less likely to be useful. Oh, sorry, I can just navigate here. Why am I doing this? Yeah, so this one is asking you for like basically to create examples where the model was getting it wrong. You might have created some instances with negations or longer sentences or so on. Hopefully that gave you an idea of where these models struggle and where they're good at. All right. Yeah, and same with the QA task. I think the paraphrase one through back translation was kind of important. So hopefully you found something that worked and you were able to recognize that having some diversity in the output of the back translation process was beneficial for getting some improvements on the augmentation. But I mean, some of you might have found strategies where your back translation outputs were very similar to the or identical, and you even got improvements. So yeah, you can't really take much away from these things. They're very empirical. But okay, so I guess that concludes the review. If you have more specific questions, feel free to come to my office hours or any of the TA's office hours to ask them. Oh, I should also mention, I mean, this will be when also specified when I release the exam, but regarding asking questions during the exam about the exam period about specific problems, we're going to enforce that all of your questions be asked as private Piazza posts, and if any of them are relevant to the broader class, like maybe there's a typo or something, then we will broadcast those answers to the entire class, but keep all of your questions private to begin with. Also, of course, this should go without saying, but don't ask for, like, oftentimes when we give these exams, people raise their hand and they're like, is this the correct answer? And they just like read out their solution. So we're not going to answer those kinds of questions. Since you have access to the internet and all the lectures and videos and notes and practice exam solutions and so on, yeah, I mean, you should only ask a question if you have some fundamental misunderstanding with the problem. And no, there will not be office hours during the exam period. That just would disadvantage people who can't make them, and the TAs will not be able to answer questions about the exam. All questions should be through Piazza. All right. So again, no class on Wednesday. Sorry, this took an hour and a half. And good luck with your exams.